Impulse is given the letter J. An impulse is a force applied for a time. When a net force is applied to an object for a time, there will be a change in the object's momentum. This can be expressed as F delta t equals delta p. And the following formula can be used whenever mass is constant. This is often referred to as the impulse momentum theorem. Let's try a few problems that involve this theorem. When being thrown, a net force of 132 newtons acts on a baseball of mass 140 grams for a period of 4.5 times 10 to the minus 2 seconds. What is the magnitude of the change in momentum of this ball? So first of all, we're going to have a ball that's being held by a person, and they're going to apply a net force to get the ball to accelerate. So its momentum is going to change. Now, since we know the force that's applied and the time that it's applied for, we can find the change in momentum for the ball. It will be given by delta p equals F delta t. Alright, so let's plug in. The change in the ball's momentum is 5.94 Newton seconds. That's another unit for momentum. Newton seconds is a unit of momentum, and it's equivalent to kilogram meters per second. Now let's say the initial speed of the ball in the question is 0. What will be its speed when it leaves the pitcher's hand using momentum to calculate it? Alright, so for that, we should use the formula delta p equals m delta v. We already know the delta p for this ball, and we know the mass of the ball. So we ought to be able to solve for the delta v. It's 42.4 meters per second. Next, a batter is going to hit this ball with a net force of 1320 newtons opposite the direction of the ball's initial motion. There's going to be a 9 times 10 to the minus 3 second contact time during the hit. What will be the change in momentum for this ball? Okay, so I'm going to draw out the problem. The ball is coming in with a momentum of 5.94 Newton seconds. It's going to strike the bat here with a very short collision time. There'll be a force applied to the ball, and then afterwards it's going to be coming back. And we don't know what that final momentum is going to be. So in order to figure it out, let's let this be the initial momentum that it comes in with. And we of course have the idea that the initial momentum plus the change in momentum will equal the final momentum. So what can we use for the change in momentum? Well, we should use the impulse momentum theorem. The change in momentum can also be described as the impulse, and that will be the force times delta t. However, in this type of problem, we want to be very clear about the direction, and we want to consider the signs of everything, because momentum is a vector. So let's go through here and put a little x on each quantity. That'll make it clear that we're going to now include the signs in everything that we do. Okay. Impulse is also a vector. So we'll do this. So whereas the initial momentum is positive, we're going to want our final momentum to be negative. We're also going to want to consider that the force being applied to our ball is going to be negative as well. Okay, so let's see. We're going to have over here 5.94 Newton seconds plus our change in momentum equals the final momentum. Let's figure out what that change in momentum is, because that is what's going to go in here. We want to multiply the force times the time. The force will be negative 1320 newtons, and the time 0.009 seconds. I get negative 11.9 for that. All right, so we're going to want to put that in here. Now we can calculate our final momentum. It just so happens to be negative 5.94 Newton seconds. So our ball comes in with 5.94 Newton seconds to the right. It contacts the bat where it feels a force directed to the left, and then the ball returns with negative 5.94 Newton seconds as it leaves the bat. All right, the final question here is, what force does the ball exert on the bat in the question above? Well, by Newton's third law, if the bat strikes the ball applying a force F of 1320 newtons, then the ball will also push on the bat in the opposite direction with 1320 newtons. That's Newton's third law, equal and opposite forces. There we go.